Hey, Honors Chem. We're going to talk today about Bohr models, and I want to start this lesson out by reviewing what an atom is. We should know what this is. An atom, the exact definition is the smallest unit of matter. But if we really think about this, there's some problems that this possesses. If an atom is the smallest unit of matter, it should be the smallest thing that exists. However, we know that within an atom, we have kind of three things. We have protons, neutrons, and electrons. And each of these kind of have their own definition. Protons are positively charged. Subatomic particles. And again, protons give identity to an element. Neutrons are uncharged or neutral. Subatomic particles. And electrons are negatively charged subatomic particles. The reason why the atom is kind of described as the smallest unit of matter, even though there are things within the atom, is, without at least one proton, an atom cannot exist. So an atom can exist without at least one proton. We know that many elements have more than one proton. In order for an atom to be an atom, it has to have a proton within that nucleus, okay? And when a proton exists, it must be in the nucleus of an atom. So it's a little bit weird to think about the fact that we can have an atom even though the atom is defined as the smallest unit of matter. The atom doesn't exist without protons. In order for a proton to exist, it has to be within an atom. So that's why this kind of gets that definition of the smallest unit of matter. I hope that does a sort of a little bit of an explanation of, yes, there are things smaller than an atom. Are they technically matter? No, they're electrostatic charges. They are kind of forms of energy, if we think of it that way. But anyways, moving on. What we're going to talk about today is the Bohr model and this idea of what atoms actually look like and where electrons specifically are within the atom. But Niels Bohr is a Danish theoretical physicist. He was credited with a finding in the development of the atomic theory. Specifically, his work kind of gave rise to understanding where electrons exist in the atom. And he proposed that electrons orbit the nucleus, which we already knew at this point, but they do this in specific energy levels that can only hold a certain amount of electrons. And we're going to talk about all of this in this video. Okay? And basically, he created what was called the Bohr model, which is a display of where electrons exist in an atom. Cool. One word that I want us to pay a lot of attention to right now is this idea of an energy level. An energy level is sort of a space where electrons reside as they orbit the nucleus. Okay, and the way that I kind of want to explain this is if we have a nucleus here, we know that the nucleus holds positive charges or protons and neutrons. Okay, this would be a nucleus of helium because it has 2 protons and 2 neutrons. It'd also be like the most abundant isotope of helium. What Niels Bohr said was around the nucleus, there is something called an energy level. Okay, and within this energy level is where the electrons for that element or that atom are going to reside. Okay. And remember, the electrons are still moving around the nucleus. So this would be kind of where the energy level is. Okay. But he also said, and this is probably the most important thing that he discovered, was that each energy level has a capacity of electrons. I know that doesn't sound right, but like there's a maximum of electrons that can be held within each energy level. Remember, electrons are negatively charged. Negative charges will repel each other, okay? So taking in that sort of idea that negative charges will repel, depending on how close they are to the nucleus or the attraction of the protons, kind of gives us a set number of electrons that can stay in each energy level, okay? For now, we are going to only focus on 4 energy levels, okay? So, in the first energy level, or the one closest to the nucleus, we can hold 2 electrons, okay? In the second energy level, we can hold 8 electrons. And that's also true for the third. And the Bohr model actually only goes to 4 energy levels. At least for the sake of this class, we're only going to do Bohr models that have 4 energy levels. And each of those can hold 8 electrons, okay? The sort of why this happens and why there's a set number is it's based on quantum numbers and based on like movement of electrons and kind of calculating that at the atomic level. But for now, this is all you need to know. Also, sometimes I abbreviate energy levels as N. So like the first one would be N equals 1. Second one is N equals 2. Third one is, I don't know why this is happens. Oh, it's weird. Third one is N equals 3. And the fourth one is N equals 4. Cool. With this information, we should be able to draw a Bohr model. There's also a way that you can calculate the number of energy levels that an element has. And that's the energy levels, number of energy levels will equal the period or the row that the element is in on the periodic table. Cool? So let's look at some examples. Let's look at 9 fluorine 19.0. Let's look at 14 silicon 28.09. And let's look at 2 helium 4.00. Okay. Fluorine is in the second period, or period 2, which means it has 2 energy levels. We could also think that if we look at the number of electrons, we would have 2 in the energy level. In the first energy level, we'd also need to have the other 7 to equal 9 in the second energy level. Okay, same thing with silicon. We can look at this. This is in the third period. So it would have 3 energy levels. If we start with 14, then 2 would go in the first energy level, 8 would go in the second energy level. 14 goes to 12 after 2, minus 8 is 4, so we would need 4 in the third energy level. And then lastly with helium, this one should be pretty easy. It's in the first period, which means it has 1 energy level. And then 2 of its electrons can fit in energy level number 1. Remember, unless the element has a charge, and you would know if it has a charge based on like what's given to you, it would say like plus or minus. Unless it has a charge, then the number of electrons should equal the number of protons because we want those positive and negative charges to balance. Let's look at an example of how to draw a Bohr model. And let's look at something like nitrogen. Okay, we have 7, N, and 14, just to make it easy. In the Bohr model, it's basically a picture of what the atom looks like. Okay? In the Bohr model, first thing we want to do is draw the nucleus. And the way that you want to draw the nucleus is just a circle. Okay? In the nucleus, we have protons and we have neutrons. Okay? Protons is 7, that equals the atomic number. Neutrons is 7 because we take this number and subtract it by this number. So the way I calculated that was 14 minus 7. You could physically draw 7 protons in here and 7 neutrons if you wanted. I know there's only 3, but you could physically do that if you wanted to. But usually what I tell people is you could just write P and N and then 7, 7. This tells me that the atom is nitrogen, and it's specifically nitrogen 14, okay? So the nucleus is really important to draw when we're drawing a Bohr model, even though we're focused on those energy levels. If you guys don't mind, actually, never mind. Second thing we want to do is count our number of electrons. Okay. Nitrogen has 7 protons, so there must be 7 electrons to balance it out. Okay. If the electrons were different, then it would look something like this, N3 minus or N2 plus. I think we should get that part. So 7 electrons, that means that 2 electrons are going to go in the first energy level and the other 5 are going to go in the second energy level. Okay? Now we can draw our energy levels. Okay. So I'm going to draw the first energy level and the second energy level. Okay. Last thing we want to do is place electrons on energy level. Okay, in this case, we have more than one. On the first energy level, I like to put them on opposite sides just because they're repelling each other. We want them as far apart as possible. And then for the second one, I always start on the top and I go clockwise to put them as far apart as possible. If there is more than 4, generally what happens is the electrons will be in pairs, okay? This could mean a lot of things. We're drawing our circle in 2D when atoms are actually in 3D. So really this means that if we have a circle and we're looking at an aerial view, or if we have an atom and we're looking at an area, I don't know if I spelled that right. If we're looking at an aerial view, it means that like one is here on the top and one is here on the top. So the best way that we kind of symbolize that is to draw them in pairs. We're also drawing them in pairs because when we talk about bonding, electrons like to be in pairs in order to form bonds, or at least that's how we show that they form bonds. So this right here is the Bohr model for nitrogen. Okay, it has 2 energy levels. It has 7 electrons, 2 in the first energy level, 5 in the second energy level. Okay. You could also do this with isotopes of nitrogen. If you had something like N16, then our Bohr model would be P7, N9. Again, protons can't change, it's still nitrogen, but the number of neutrons changed. And again, it has the same number of electrons. So the only thing that tells us that this is an isotope of nitrogen is the difference in neutrons. Cool. Last thing that I want to go over is if we had sort of a charged element, or what we'll learn is called an ion. How we want to kind of display this is you'll get something that looks like this, S+. Okay? This positive charge should signal that we have more protons. And specifically, we have 1 more proton because it's +1. So let's just count them really quick. If we're looking at sulfur, we have 16 protons, 16 neutrons because the atomic mass rounds down to 32. And then electrons, we have 15. We can draw our Bohr model by starting with our nucleus. We have 16 and 16. I already know that I'm going to need 2 in the first energy level. That brings us to 13. 8 in the second energy level. That brings us to, why can't I do this math? 5 in the third energy level, and the last 5 will go there. Okay, so we got 1, 2, 3. Be careful that your first energy level is actually drawn. Don't put it on the nucleus. That's a bad thing to do. 2 in the first energy level. Again, I go clockwise. And then once I hit 4, then I start putting them in pairs. Again, they're not like literally right next to each other. They're just on opposite sides of the sphere. And then on the last energy level, or the third energy level, I'm going to put 5. Cool. This is the Bohr model for S+. One thing that we want to pay attention to is the idea of paired and unpaired electrons. I don't think this is on your homework, but I want you to observe paired and unpaired electrons will occur on the outermost or highest energy level. And in this case, we look at our n equals 3. We have one pair of electrons. Uh-oh, did I not draw one? Should have drawn one here. So we have one paired set of electrons, and then we have 1, 2, 3 unpaired electrons. Cool. Again, this is kind of an intro to bonding and how that kind of operates, but we'll talk about that as we kind of go through this unit. I'm going to have another video kind of connecting Bohr models to what we learned in 3.1, which is the atomic spectra, so stay tuned for that too.